Alright, in this video, we'll start with an inner product space, and we'll see that using that inner product, we'll be able to define lengths and distances and a bunch of what we wanted. So first, if I have an inner product space, so that means V is a vector space, and this is an inner product. So first, for any V in V, the norm, the length, so I'm going to take the length of V to be the square root of VV. For this to make sense, I need to ask that all of these be positive, which we did in property 4. So that's the length. Then if I have a length, I can use it to compute a distance. So for any V and W in V, the distance so let me use D VW. That's going to be the length of V minus W. So V minus W, if you had vectors, V minus W means this vector, and the distance between the endpoint would be the length of this vector. That's why we define it this way. Alright, so that means the square root of V minus W dotted with V minus W. Alright, so it's going to match the distance between 2 points in Rn quite nicely. And then the third thing I have, once I have length, I could talk about the unit sphere. I'm gonna, so S of V, it's gonna be the set of all vectors of length 1. So set of all V and V, so that the length of V is 1. And then all of these vectors of length 1, we'll call them unit vectors like we did in Rn. So all elements V in V, so that the length of V is 1, are called unit vectors. So I have unit vectors, I have unit sphere, and I have length, and I have distance. One thing to note here is all of these length, distances, and unit vector depend on a choice of inner product. If you change the inner product, you'll change the length of the vectors, you'll change the distance, you'll change the unit sphere. So it's not something that's intrinsic to the vector space. It depends on a choice of a dot product or of an inner product. So note with the example that we finished in the last video, let's try to compute some lengths. So we had length of VW was 1/9 V1 W1 plus 1/4, V2 W2. Alright, let's say I want to find the length of the vector 3/8. For that, I'm going to need to find the inner product of v with itself, and then afterwards I'll take the root. So here I'll have 1/9 times 3 times 3 plus 1/4 times 8 times 8. So that's 1. That's 64 divided by 4. That's 16. So I get 17. So the length will be the square root of that. Which is root of 17. All right, let's find the distance between two of them. Alright, so like we said, to find the distance, you have to look at the difference and then take the length of that. So V minus W, that will be 4 minus 5 minus 2, 3. So that will be 2 minus 8. Then I have to look at the distance. The length of that, so I'll need to take the inner product. That'll be 1/9 2 times 2 plus 1/4 minus 8 times minus 8. So I'll have 4/9 plus 16. So 144 plus 4/9, which is 148/9. So the distance is the root of that. So that'll be square root of 148/9. I want to try a problem next that's a lot like a problem you would have seen in linear 1, but now in a general vector space. So let's say that I know that the length of V is 2, the length of W is 5, and the inner product is 6. And I want to find the length of 2v minus 3w. So we gave you tons and tons of these in linear 1. We could give you the angle between v and w to figure this out. We could do all sorts of things. And then you need to figure out this length by remembering that this is the square root of the dot product and then exfoiling the dot product. We'll do the same thing here. So if I take 2v minus 3w and multiply it by itself, then I'm going to start using the properties of the inner product to FOIL it. So let's see, I can distribute it. So I'll have 2v minus 3w, and I'll have minus 3w, 2v minus 3w. Then I'll distribute on the second vector, so 2v, 2v, plus 2v minus 3w, plus minus 3w, 2v, and finally plus minus 3w, minus 3w. Then I can take out all the constants. So I'll get 4vv plus minus 6vw minus 6wv plus 9ww. Now I'm going to use the fact that vv is the length of v squared, ww is the length of w squared, and vw, wv are the same. So I'll get 4 times the length of v squared minus 12 vw plus 9 length of w squared. And now I'm ready to plug in everything I have. So 4 times 4 minus 12 times 6 plus 9 times 5 squared. So I get 16 minus 72 plus 225. So 25 times 9, 45, 18, 225, yep. So what do I get? 225, that's 241 minus 72, I get 9, 361, 169. That's not what I'm asked. I'm asked for the length. I found the inner product with itself, so I still need to take a square root. So the length of 2v minus 3w is square root of this, of the inner product I just found. And so square root of 169, which is 13. So all of those things that we did in linear 1, we can do exactly the same thing here. This is like a generalized cosine law. And last problem, I want to sketch the unit sphere in V and R2 with this dot product. So in R2 with the usual dot product, we do actually have the real unit sphere, but in this one we'll get something different. So what will we get? Well, we want the length of a vector to be 1, so that means the length squared should be 1 as well, so 1/9. So that's 1/9 of V1 plus 1/4 of V2. And so I get 1/9 of V1 squared plus 1/4 of V2 squared should be 1. And it's easier to see what it is if you use x and y. So this is what I get. This is an equation you should remember from high school or seeing something similar to this in high school. This is going to give me an ellipse. It's going to give me an ellipse. If x is 3, that's going to be my x-intercept. For y, I'm going to need 2. And so -3 -2. So my ellipse will look something like this. So this inner product is not very different from the old one. It just changes, instead of having real sphere, they're a bit stretched, so the weight of x and y is slightly off, but not much. It doesn't look too different.